Ladies and gentlemen, please welcome AACP President-elect Patricia A.
Good morning. Well, that was kind of poor. Let's try again. Good morning. Oh, you're good. Okay, I hope everyone has enjoyed the beginning of this year's annual meeting, including Saturday evening when we celebrated 10 extraordinary years of the Academic Leadership Fellows Program, as well as last night's opening reception. There are so many opportunities at this meeting to continue our learning and networking, including this excellent session. Since 2004, AACP has dedicated this session to a wide range of topics of scientific importance to our profession, including last year's focus on pharmacogenomics. I am particularly pleased with the program committee that the program committee identified the issues associated with big data for today's program. As I noted in my remarks yesterday at the House of Delegates, this is the focus of the 2014-15 Argus Commission's work. Before I introduce our outstanding speaker, we have 2 scientific awards to present. And my dear colleague, AACP President Peggy Piazak, will do the honors. I'll turn the podium over to Peggy.
Thank you, Pat. It's a true pleasure to lead the celebration of our latest Volwiler and Dawson Award winners. I'll begin with the Volwiler Research Achievement Award. This award was established in 1977 to recognize outstanding research by a pharmaceutical scientist and educator, and is named in honor of the late Ernest H. Volwiler, former president and research director at Abbott Laboratories. Today we honor Dr. John Pizzuto, founding dean and professor at the Daniel K. Inouye College of Pharmacy at the University of Hawaii, Hilo. Dean Pizzuto has been on the forefront of cancer chemoprevention for the duration of his 35-plus-year scientific career. His many discoveries offer real promise to the goal of ultimately reversing the currently escalating rate of new cancer diagnoses. This could spare millions of potential cancer patients and their families from the physiological, emotional, and economic challenges of aggressively treating the disease. One of John's signature contributions is in the elucidation of the health benefits of the natural product resveratrol, which is a deceivingly simple still bean structure found in grapes, red wine, thank you, John, antioxidant berries, dark chocolate, many thanks, John, and nuts. It has a multitude of physiologic activities, many of which may be beneficial in cancer chemoprevention. Dr. Pizzuto's research team was not only the first to identify these potential therapeutic benefits, they have generated a multitude of resveratrol analogs designed to target specific receptors and thus enhance the potency and selectivity of chemopreventive action. His work is also focused on optimizing the metabolic profiles of these analogs to promote safety as well as prolonged therapeutic benefits that often foster patient adherence to therapy. Dr. Pizzuto's groundbreaking discovery of resveratrol's therapeutic potential has informed the work of myriad scientific teams around the world. This, in turn, has resulted in the publication of over 5,000 manuscripts and monographs and prompted the establishment of numerous grant programs, clinical trials, and companies. The profound positive impact he has had on the careers of the many scientists now working in this targeted research area, as well as the broad area of cancer chemoprevention, would be impossible to quantify. He continues to foster quality and innovation in chemoprevention research by serving on NIH study sections and as a project reviewer for many national and international granting agencies. Would you join me in enjoying a brief video interview clip featuring Dean Pizzuto while John joins me on stage?
Nothing has been as gratifying as receiving the Volwiler Award from the AACP, and I think nothing ever will be. Collaborative research has been a key. We've been able to create synergistic relationships through collaboration, and really no one has really been able to match that, and that again provides a competitive edge. So really the key is perseverance. And of course it doesn't hurt to have some ingenious ideas too. I think it's important for university administrators to create a vision and an environment where the faculty and the staff and the students have really a sense of pride and the ability to live their dreams. So looking back, I may have had a misspent youth, but I've strived for excellence every day of my life since I was about 18. So in my view, you can shoot for a star, maybe you'll end up in the moon, but at least that's better than Hoboken.
John, here is a surprise from your colleagues from your institution.
Thank you very much. This is a huge surprise, and I guess you all know that I'm not welcome at Hoboken anymore. So it was a great day when I was notified of receiving the Volwiler Award, and then shortly thereafter I received another surprise, and that was to make this video that you just saw an excerpt from. So I hope you liked the video, but if you didn't like the video, feel free to blame Lucinda. In any case, you've heard quite a lot from me, so although it's dangerous to hand the podium over to any dean, I assure you my remarks will be short. So receiving the Volwiler is definitely one of the most gratifying experiences of my life, and I'm very grateful to everyone who prepared the nomination and supported the nomination, and of course the Volwiler Selection Committee and the Board of Directors of AACP. And very often at times like this, awardees thank their families, their students, their postdocs, their collaborators, and of course they all had a lot to do with this, and I am very grateful. But what I'd like to do in the next couple of minutes is to acknowledge 4 good friends and 4 colleagues who had a very strong influence on my life, who unfortunately are no longer with us, but each of them changed the world in very positive ways. And the first person I'd like to mention is Gordon Skvoda. I believe Gordon is best known for his discovery of emblastine. And once I asked Gordon if this natural product drug discovery was through serendipity, and Gordon told me, no, it wasn't serendipity at all, it was his intuition. And I have to admit that Gordon had a few adult beverages, and so did I, but that's always stayed with me. And later on, I had the opportunity to ask another good friend and colleague, Monroe Wall, pretty much the same question. I asked him, Monroe, was the discovery of famous drugs like Taxol and Camtothecin serendipity? And he gave me the exact same answer. He said it wasn't that at all, it was his intuition, and that it was exactly the same answer, and that's always stayed with me. So I think that that's probably a message to everyone in science to rely on your intuition. It's very key. And next, I'd like to mention Norman Farnsworth. Norman was a good friend and colleague for many years at the University of Illinois, at Chicago. And I was always jealous of Norman because he's the only person I know who behaved a lot like an 18-year-old when he was almost 80 years old. And it was a great spirit, but Norman really embraced the concept of collaborative research, and I think collaborative research is really a key that's made a big difference in my life. And lastly, I'd like to acknowledge Richard Moon, who recently passed away. And Dick was really one of the original pioneers in chemo prevention. I think that I've gained a strong passion for chemo prevention. And I hope that, that you can bring some of this to your classes, to your students, and to the future of pharmacy. But Dick taught me many things, often over a glass of good scotch, with I hate to admit it, but a good cigar. So these are 4 people who I'll always miss. And I'd like to change the topic a little bit and pick up just for a second on what Peggy said, and that is I would like to acknowledge Vitis vinifera, the common grape. So in all of the joy and glory of nature, the grape was wise enough to produce resveratrol, a very simple compound, but one that we were fortunate enough to discover the biological activity of. And we published many papers, but our original paper was cited many, I guess, thousands of times, and that in turn led to a large H index for me. And here we are in Texas, so bigger is better, so having a good H is good. And somehow or another, it seems especially fitting to receive this award in Grapevine, Texas. So tonight, if you have the opportunity to have a glass or 2 of red wine, I suggest that you toast to the power of natural product research. And lastly, I'll make just a very brief announcement. And you notice now I have a lei, but I do not have an aloha shirt. An aloha shirt, is the formal business attire of Hawaii. And maybe some of you have heard a rumor, and I can confirm that rumor is true, that actually what I'm doing here in my suit is practicing for my next position of dean at Long Island University, which I'll assume the beginning of next year. So no more aloha shirts. I do have a large collection for sale. I probably made a mistake when I left Purdue. I gave all my ties away to the other deans, but this will be my new life. So in sum, I've had the opportunity to live in paradise. Now I've received the Volwiler Award, and next I'll be moving to what I personally consider the center of the universe, New York City, so how lucky can one person be? So thank you very much, and I do hope that you will tell Lucinda you did like the video. Thank you.
Our second award this morning is the Paul R. Dawson Biotechnology Educator Award. The award is endowed by Amgen in honor of its former Vice President of Marketing and Sales, Paul R. Dawson, a staunch supporter of education in biotechnology. Since 1993, the award has recognized an active scientist within the ranks of pharmacy education who is a leader in the contemporary teaching of and scholarship in biotechnology and its related science. This year, we recognize Dr. Anil Gulati, Professor and Associate Dean for Research at the College of Pharmacy at Midwestern University, Chicago. It is striking that his nominator first notes that Dr. Gulati is a dedicated teacher, as well as a gifted and generous mentor. He routinely includes students in his research. Dr. Gulati's research contributions are also impressive, contributing to 32 patent applications and inventions, almost 300 research publications, and numerous honors and recognitions. The focus of much of his work has been on endothelium. Let's look at a brief video interview clip featuring Associate Dean Gulati while Anil joins me on stage.
Paul Dawson Award from AACP means a lot to me because this award brings international recognition to our work. Our team has been working in the field of endothelin for past several decades, trying to generate novel ideas which can be developed into products for the benefit of patients. As I mentioned earlier, that I was fortunate that I got opportunity to work in India, Europe and United States. The cultural differences in various countries taught me to dream big, work hard to achieve those dreams, and be prepared for failures and be persistent. One thing I'll tell you that I have learned all this at a late stage in my life, and my aim is to teach my students that they should gain from my experience and start the process early in their life.
We have to shake hands first and then get the award because it's so heavy.
Thank you very much, AACP, and my nominators and all the persons who worked very hard in this process. And today we are celebrating success which is based upon a lot of people. I'm here on behalf of many, many who have helped me reach this stage. And we celebrate success, but behind success, there are a lot of failures too. And I can tell you there are many times when we encounter failures in the sense that we have an hypothesis and it is not working. We think that, oh boy, this is not working. I don't know what stage next will be and all that. And that reminds me of Eric Clapton's Unplugged, which, although I don't have the guitar and I can't sing also, but he very elegantly said that nobody knows you when you are down and out. And then in that very album, he also remarks that when you get back on your feet, everybody wants to be your long-lost friend. But the gap in between is who gets you on the feet. And that is the support system which gets you on the feet. It's the family, it's the institution. And I'm so grateful that I came from India and I was greeted at University of Illinois. Dr. Henry Manassi, he made sure that I joined the faculty within 6 months of my arrival. And then for a few years, many years, I worked at University of Illinois. And then Dr. Lee from Midwestern University, she greeted me with open arms and said that, Anil, you move on and come and join Midwestern University. So Midwestern University gave me a platform which I couldn't believe that they allowed me to set up the structure in such a way that we started doing research, making inventions, one after another, and they gave us the flexibility to move our products from academic into industry. And today I can very proudly say that with the help of all these support staff and the institution, we have at least 2 phase 3 clinical trials going on based on our patents. And there are 2 phase 2 clinical trials going on. And there are at least 2 or 3 phase 1 clinical trials are going on. So I'm very fortunate that in spite of having so many failures in my research and hypothesis that we have been able to achieve. And it is all because of teaching of my gurus and that be persistent, you fail, be persistent, keep on working towards the projects which you have, and ultimately success will come. So, and in order, I'm so thankful today that our university president and executive vice president are here to celebrate this occasion, and they have made a special trip to come here. I'm so thankful to you, and I can't be more happy than having an institutional success and the family support. My wife, my brother and his wife, they are all here to, so it's all because of support that we have been able to achieve this. And lastly, but most important, is our Vice President, Dr. Lee, and our Dean, Dr. Nancy Furtoff. The environment in CCP is such that it is like a family. It's so homely that you don't even feel like that you are going to work, and you enjoy every day when you, so that's the best I can have. And thank you very much for AACP for giving me this honor. And I'm grateful that I'm joining all the stalwarts like Rodney Hope, Tejal Desai, and many, many others who have received this award in the past. So thank you very much, and I'm grateful to all of you. Thank you.
Hearty congratulations to John and Anil, our most worthy award recipients. Now for a keynote presentation. As noted earlier, the 2014 Program Committee considered a number of potential topics for this year's Science Plenary. Drawing upon the work of the 2012-13 Argus Commission, which studied game changers in research, healthcare, and health professions education, the committee identified the construct of big data and the impact of information technology as cross-cutting issues that will likely impact every aspect of our future work. I am very pleased to introduce Dr. Atul Butte, Chief of the Division of Systems Medicine at Stanford University. He will share his insight on who is collecting this data, what they're doing with the information, and what it means for healthcare. Please help me in welcoming Dr. Butte. I can hardly wait to see you.
Great, thank you. Thanks for having me here. It's a real honor to be able to present to this audience. If I can get my slides up. Let's see if I could tell a couple of jokes, but I don't see the slides here. Let me just make sure you're not seeing them here. No slides yet. Anyone in the back? There, let's go back a little bit here. No delusions yet. All right, thank you very much. And first and foremost, I want to just convince you I'm a medical educator and a medical researcher first, okay? So I kind of a kindred spirit in some kind of way. And from one medical educator to a bunch of others, I got to obviously start with my disclosure slide. I've founded a bunch of companies. I consult for a bunch of companies. You probably don't want to believe another word I say over the next hour, so I wouldn't blame you. But actually, all humor aside for a second, I'm most proud of the bottom right corner. So for some people, this is a slide of shame. This is my slide of significance, actually. More than half of my graduate students now have started a company, whether they go into academia or not. And they do this with the most amazing technology platform in the world, and it's big data. And I'm going to show you how they do it, how we do that, and maybe I can convince some of you that this is the most amazing time ever to be in biomedical research, despite all the negative news you hear. So obviously, we're in the middle of this data deluge. The Economist magazine had a special issue of called The Data Deluge, this guy with this upside-down umbrella collecting ones and zeros. It's raining ones and zeros. The human species now generates 2 zettabytes of data every year. Zettabytes. What's a zettabyte? If you forget your metric prefixes, it goes kilo, mega, giga, terabyte, petabyte, exabyte, zettabyte. 2 of them. And next year, of course, we'll generate 4 zettabytes of data, right? Because it's growing exponentially, doubling every year. Now, I'll be the first to admit most of these zettabytes of data are these YouTube videos of kittens playing with pianos and yarn. Perhaps entertainment value, not much scientific value, but there's some value nonetheless. But there is obviously scientific data in these zettabytes as well. So to give you an example, the Large Hadron Collider generated petabytes of data to come up with new particles, new subatomic particles in physics. A couple weeks ago, you might have seen NASA now says that they will have so many telescopes looking at the sky that they are generating exabytes of data every day, okay? Every day, an exabyte of data. Now, there's something telling about NASA and these exabytes. They're generating so much data now with these telescopes that there are not enough astronomers to look at this data, right? You're going to hear this theme again. They generate so much data that they open it out to the internet, so citizen scientists can come and say, well, that's a galaxy and that's a star. You don't have to even be a trained scientist. They'll train you how to do this. That's that much data that they just give it away on the internet today. And that's happening in biomedicine as well. So obviously, the next big scientific revolution is thought to be data-driven sciences. There's a great article if you're really looking into business perspective in Harvard Business Review. Nature says it's shameful if we don't take advantage of this data. Science says we need to make this data maximally available. And even the Lancet says if we don't start to share research data, it's an impediment to public health. And collectively, I'm going to call this big data. I don't really like this buzzword, but everyone uses it. Everyone knows there's a lot of data out there. It's probably going to go away at some point, but let's use big data for the scope of this talk here. Now, what kind of data are we talking about here? And where does it come from? Well, it comes from mandates to share this data. And some of you might have heard, for example, last year that the White House announced. The White House announced that the publications that we write as academics, if we're funded by the NIH or Department of Energy or Department of Defense or any government grantee, we now need to make our data, our publications accessible to the public within a year. And some people thought a year was too long, and some people thought a year was too short. But within a year, our publications need to be open to the public. Most of you probably heard of that. Those of us funded by NIH, this was a non-event. We already had this here. But all the way in the fine print, in the footnotes, they said, oh, by the way, you need to make your data available too, not just the papers. You got to make your data available too, because we want to see what you're doing. This trend started with the journal editors. It started with the reviewers. We can't see what the writers are doing, what the manuscript authors are doing. It started with the editors, then it goes to the funding agencies, and then it gets to the government. You're going to see this trend again and again. So what is this kind of data? What are we talking about? This is my favorite example of this kind of data. On the left here of this slide is an Affymetrix gene chip. I'm not connected to the company Affymetrix, but I love this chip. Okay, for those of you who have never seen one in person, this is what it looks like in my hands here. It's a neat looking chip. This chip, it's from a company called Affymetrix in Santa Clara. They share the same town as Intel. So obviously they kind of make this look like an Intel microprocessor. There's nothing electronic here. It's just one of a myriad of high throughput technologies we have in biomedicine today. That little grid there in the middle of that chip is the size of your thumbnail. You can see a thumbnail at the bottom. And this particular technology just measures all the RNA, all the genes in the entire genome. How much are turned on, how much are turned off. On the right, when you get tired of measuring them one by one, we measure them in a 96-well plate. We obviously love these 96-well plates in the lab, and now every well here is its own chip. Now this is still an amazing technology to me. I mean, when I look at this chip, it's just astounding that we can measure the entire genome. It's even more astounding to me that this probably only costs about $200 or $300 now. You put a sample of cancer, diabetes, whatever, mouse model, you're measuring the entire genome for a couple $100. Actually, that's not even the most amazing part. This is already a 15-year-old invention. We've had these for 15 years. The most amazing part of this chip is that we make scientists share this data on the internet today. That's the most amazing part about this. It started with the journal editors, then it went to the funding agencies, and then government got involved. You have to share this data. So what does that actually mean? Fast forward to August of 2012. August of 2012, just 2 years ago, we reached the magic number of 1 million of these chips publicly available. We got 1 million of them on the internet now. And you can see the growth curve right in the front there. This is an article in Nature about this milestone. Now, if you have really sharp eyes, you can see, boy, it kind of looks like it's slowing down there in 2012. What's going on there? And then you realize they only counted half the year, right? This came out in August. Still doubling every 2 to 3 years. In fact, if you look right now, I just looked this morning, we're actually just shy of 1.5 million of these chips publicly available. 1.5 million of these samples already available. Just in the scope of this hour, we're probably going to add 100 of them. Now, what does this really mean? What are these chips? What do you do here? In the middle of this website here, I'm showing you the 2 websites you can get to this data. One's at the NCBI, run by the NIH. One is called Array Express. It's run by the Europeans. You can see even in the back, you see there's a little search box there. Now, you could come in. Oh, forget about you. A high school kid that needs to do a science fair project. She can actually go to this website. Let's say she wants to study breast cancer. She can type in breast cancer, hit search, and find and download 44,000 samples of breast cancer for her science fair project, about as easily as she can find a song on iTunes today. What an amazing concept. A high school kid can find and download 44,000 samples, digital samples of breast cancer already run. Now, if you haven't figured out why that's magical for a moment, let me just explain. The one kid who can get to the data in the database has more samples of breast cancer now than any breast cancer researcher, because that one breast cancer researcher has to share his or her data along with his or her competitors. And the kid who gets to the data in the middle now has it all. And if for some reason 44,000 samples aren't enough for you, just wait 2 years, it'll be 88,000 samples. What an amazing world. It's adding even as we sit here, right? Now, actually, the number I like, it's even harder to see here, is 1,800. 1,800 labs have already shared this data on the internet. Okay, 1,800 independent labs. Now, let me explain how amazing that concept is. Let's say I'm a brand new breast cancer researcher today, right? I'm inspired by people who've had breast cancer. I want to study breast cancer, but I'm starting from scratch. You are all, in the audience here, my review committee for the grant I'm about to write. Here's the grant. I'm going to get my friends on the internet to help me study breast cancer. We call that crowdsourcing today. So I'm going to crowdsource breast cancer. And I'm going to get 1,800 of the best labs in the world to run the best technologies in the world on their best characterized patients in the world, and they're going to all give me that data for free. Now, if I propose this to you in a forward direction, you would laugh me out of the review committee room, right? Why would anyone share data with you for free? Yet, here it is. 1,800 labs, the best ones in the world, get all the funding, put all their data out there for free. So when I think of this kind of public big data, I like to think of it as retroactive crowdsourcing, okay? 1,800 labs are there in the world to help you, and they don't even know it. Oh, and by the way, 1,800 labs are there to help you, and you don't even know it. And still, it keeps doubling every 2 years. What an amazing world, an amazing time to be in science today. Now, for those of you who doubt a high school kid can actually do this, here is the high school child who has done it. This is Brittany Wenger from Sarasota, Florida. I've yet to meet her. She was in high school. I guess she goes to Duke University now. And at age 17, she downloaded data off the internet and was able to come up with a neural network, a machine learning diagnostic for breast cancer. And she won the top prize in the Google Science Fair competition as a high school kid. And then I guess she got bored, so the following year she was in all the headlines because she did the same thing again for leukemia. Okay? High school kid. Now, obviously, what I'm saying is if a high school kid can do this, we all have to be doing this in our own universities and campuses and institutions too. The data is sitting there. There's no reason to ignore it. For some reason, we have this kind of mindset because we think of YouTube videos. We think if it's free and on the internet, it must be valueless, right? How could there be any value to this? Yet this is the most valuable data in the world, but we make scientists share it. It's all open to you. So, but even high school kids can do this. So let me just talk about a couple stories about what I do with this data in my lab and how that's led to even pharmaceutical discoveries and where I think things are going next. One way I like to introduce one of my stories is to promote this guy, Linnaeus. Some of you remember Linnaeus from elementary school or high school. He's a guy who gave us the binomial nomenclature. Remember kingdom, phylum, class, order, family, genus, species? You all had to know that on a test at one point, I'm sure of it. Some of you had mnemonics, right? Some are clean, some are dirty. You don't have to repeat them here. But everyone had a way to remember that. Kingdom, phylum, class, order, family, genus, species. Well, Linnaeus is the guy who gave us that, right? Homo sapiens, mus musculus. He's the guy who put species into a tree, a taxonomical tree. Now, if you want an example of a 300-year-old tree, Linnaeus was born about 300 years ago. On the right there is an example of a 300-year-old tree. I was visiting Tokyo a couple years ago, and when you're jet-lagged in Tokyo, the thing to do is see the famous fish market where they're throwing fish around at 2 in the morning. And right next door there is the Hamariku Garden. In the middle of this garden, this sign says it's a 300-year-old pine tree. And I was thinking about Linnaeus. I was thinking about this tree being the same age as Linnaeus. I noticed the one thing about this tree is all the crutches. You need a lot of crutches to keep trees alive at 300 years. I was thinking the same thing for Linnaeus' tree, right? Linnaeus built this whole species and put all the species in the right place. But today, actually, we don't trust our eyes. We trust DNA, right? With all due respect, Linnaeus, this species looks like these species, but the DNA looks like that. So we move species all the time. And for the clinical folks in the audience, which I know there are many, we actually do this for clinical relevant organisms too. Pneumocystis carinii, PCP pneumonia, remember AIDS-related pneumonia? In 1999, we renamed it to Pneumocystis jirovecii because we got the species wrong. All this is a long introduction to something else Linnaeus did that nobody remembers. Nobody remembers about Linnaeus. Linnaeus was actually the first guy to put diseases into a taxonomical tree as well. Okay, before that, we made lists of reasons why people died, and he put it into a tree. And the word for that is called nosology, right? It has nothing to do with your nose, right? Nosology is a systematic classification of diseases. On the right here, you can see how crude it was. Let's put the painful diseases there. Let's put the fevers with urinary problems here. And in the middle, let's put fevers with heavy pulse and topical pain. He's not remembered for this because the poor soul got it all wrong. Why would you remember him for this instead of the species? But we started to think about this. If we so eloquently now move species around into species trees, why don't we move diseases around into disease trees today? Well, disease trees still live and breathe today, right? Disease trees started in 1763 with genera morborum, but today, what do we call this? We call this the ICD, the International Classification of Diseases. Some of you know we're still stuck on ICD-9. Some of our systems are on ICD-10. We're arguing about whether to go to ICD-10 or move to ICD-11. ICD started in 1860, okay? 1860, we're using like the 10th edition of something that started, a little after the American Civil War. That's how bad it is, right? Well, it's kind of easy to pick on Linnaeus, but let me just show you what ICD-2 looked like 100 years ago, okay? So this is the Manual of the International List of Causes of Death. This is how nosology moved on after Linnaeus. This is the second revision, so this is ICD-2, Paris, 1909, so about 100 years ago. You can get these books on Google Books. It's amazing when you look at these ICD systems, right? It's written the same way our current code books are written. Let's use code 39 for cancer of the buccal cavity, cancer of the cheek, right? Code 40, cancer of the stomach and liver, cancer of the intestines, female genital organs, breast, skin, and then this book does what we still do today. We're running out of numbers, enough with the cancers. Put all the rest in 45, right? We're running out of numbers here, right? Including lung cancer and brain cancer. Not worth distinguishing from each other 100 years ago. Isn't lung cancer the #1 cancer killer today? Was cancer not otherwise specified 100 years ago? It's amazing how much you can learn about medicine looking at what we put in not otherwise specified. It's all the stuff we're embarrassed to really talk about, right? So that was code 45. Code 50 is diabetes, right? I'm an endocrinologist. Banting and Best is still 10 years from here. So there was no distinction of type 1 or type 2, including my entire field of endocrinology did not exist. They were all under general diseases. I guess the general doctor had to know endocrinology back then. All of them, except for code 88, disorders of the thyroid gland, okay? Now, some of you might know, most of you know, the thyroid gland sits right here in the throat. I guess if it gets so goitrous, so big, I don't know, I guess it can block the trachea. They put it on a respiratory disease, right? It has nothing to do with how you breathe. It just happens to be sitting on you get the point here, right? They had no idea. Smallpox, cholera, plague, glanders, anthrax, some of the lowest codes in the book, they were just prevalent. If I had a single case of that in my hospital, I'm pretty sure Homeland Security would be there by the end of the day. And literally this international standard, you can see at the bottom, has to say, if you have a patient that died because of a visitation from God, use code 189. International standard, right? But the same way you're laughing at this, can you imagine how they're going to be laughing at us? Forget about 50 years, 20 years from now, 10 years from now. those silly fools didn't know that this joint disease and this bowel disease were the same thing, right? They're gonna be laughing at us. So we said, instead of just fixing, let's come up with a brand new nosology. Let's just create one from scratch. And you know how we're gonna do it? We're gonna use all this public data. We're gonna use all these chips to do this. So we just started to collect. My first big NIH grant is go get every human disease studied with these chips. Just go get them all from all over the world. And so we built this big grid of hundreds of diseases going up and down and tens of thousands of genes going left and right. We start to color code all the genes. You know, does it go up? Does it go down? How much? And we start to sort this out, and we start to get curious findings here. You know, there's certain diseases that look like other diseases. One of my favorite ones is muscular dystrophy. Seems to look like having a heart attack. Well, that's kind of interesting. Well, muscular dystrophy we take care of in the children's hospital, right? And the heart attack we take care of, the adult cardiologists take care of at the adult hospital. These doctors don't even see each other, maybe not even in the same cafeteria, right? But the molecular processes are so similar. Well, how do we take advantage of that? And then we start to realize we have almost 40 drugs to treat heart attacks. And we have close to 0 for muscular dystrophy. Boy, if these diseases are so similar to each other, why can't we start to share drugs with each other? And we started to get interested in finding new drugs using this public data. Now, why would we want to do this? I think this audience knows. In fact, it's kind of amazing. If you ask lay Americans, the lay public, how much does it cost to develop a drug? They pretty much answer it's $1 billion. It's amazing. Most Americans don't know much in common, right? But they know this number. It's $1 billion to develop a new drug. It takes 10 years. Actually, it doesn't cost $1 billion. It's an underestimate, as you all know. The correct number to generate a new drug is just pharma R&D dollars divided by the number of new drugs, right? It's very simple math. If you do that math, it actually costs between $4 billion and $12 billion to develop a new drug. This is from Forbes just a couple years ago. This is not changing. Again, with all due respect to any of the company representatives here in this audience, kind of find it funny that Pfizer in the middle there at $7 billion, I think is trying to acquire AstraZeneca at the top at $12 billion per drug. If I were in the middle, I'd probably want to buy a company lower than me, not higher than me. I don't know, that would just be me. But I'm not sure why they're going to a more expensive company here. Now, all this would be okay, I guess in some weird world, if it were sustainable, but this is not sustainable anymore. And whether you like the pharma industry or not, you probably like the pharma industry in this audience, we're heading to 2018, what some theorize to be the patent cliff. So many drugs are coming off patent, which to me is still a good thing for society, but so few new drugs are coming out that in 2018, it's theorized the entire pharma industry is going to lose $250 billion of revenue. I didn't say $250 million, I said $250 billion of revenue, less revenue that year. Now again, you may like the pharma industry, you may hate the pharma industry in this audience, so I'm not passing judgment on them, but I'm kind of worried. If they're losing $250 billion, where is the next big drug we are going to need? Because we have plenty of patients that still need drugs here. And then I realized it's gonna all come down to us. In this audience, it's gonna come down to me, it's gonna come down to our faculty, our researchers. And we have to challenge this aspect that it's gonna cost $1 billion to develop a drug. It just cannot do this anymore. So we're gonna have to come up with new ways to do this. And so we start to realize, why don't we use all this public data to do this? So we start to collect public data. And I already said on the left there, I showed you that we collect diseases. And so what I'm trying to show you here is we collect experiments where people looked at diseased individuals and healthy individuals. So we've got disease, run a chip, healthy, run a chip, and figure out what the difference is across the genome. So with disease, without disease. On the right, we've got lots of people studying drugs in the context of cell lines. They take cell lines with the drug, without a drug, with the drug, without a drug. A lot of this comes from the Broad Institute, Whitehead Institute, many other researchers now studying just machines, robots just testing drugs and drug screening. So on the left, we got with disease, without disease. On the right, we got with drug, without the drug. And we get the kind of insight to put these two together. The reporters on this call this Match.com for drugs. Okay? Now, some of you might not know Match.com is how more younger folks now than you would imagine, that's how they find mates, right? Or at least dates. Maybe you end up marrying the person, right? Match.com is how you put partners together, right? And what's the famous saying? Opposites attract. And that's the same thing here. So what do? We just take a disease, and if this gene goes up, and if this gene goes down, and then on the right, I got a drug in my library that makes this gene go down and this gene go up, well, maybe there's a match there, right? I'm trying to reverse the effects of the disease. And that's with 2 genes, imagine 20,000 genes. And you get the idea. I don't need to show you a formula. You figure this out. The drug has to reverse it. It might not be perfect, but we're going to take it forward. And where we're going to have the most fun doing this is not to figure out the new drugs, because we have plenty of new drugs in our kind of theory here. But we get a lot of fun doing this with existing drugs, finding new uses for existing drugs, right, or drug repositioning. This audience obviously knows the classic hits in drug repositioning. I think one of the earliest ones, if you count just drug repositioning, I think it comes down to that cardiac drug with hair growth as a side effect. Of course, that's minoxidil. Of course, everyone, even the lay public, knows the story of the other cardiac drug with the other interesting side effect, which of course is Viagra. I think even this audience knows that Viagra has done a double switch. We also have Revatio, same molecule, but I think it's indicated for pediatric pulmonary hypertension. So when the blood vessels from the heart to the lung get constricted, it opens those blood vessels up too. And all the papers came out saying kids on Viagra, babies on Viagra. We know all the jokes there. But you know what? Instead of finding these by accident, how about we find them on purpose using public big data? And so we do this, and we start to turn our crank, and we start to get ideas. And we start to get ideas. And one of my favorite ideas, one of the best ideas, turns out to be an epilepsy drug we predict works on Crohn's disease. Now, these are my famous rat colonoscopy videos. If you're not chuckling yet, think about those 2 words together, right? Rat colonoscopy. Many of you over age 50, you know what a colonoscopy feels like. So this is a rat colonoscopy. And I have a whole story on how we get this by finding companies to do this for us. But on the left there, you see what a normal rat colon looks like. I'm sorry, this is before lunch. In the middle is a rat with inflammatory bowel disease in the middle. And then on the right is a rat treated with a particular epilepsy drug called topiramate. It's a seizure drug. And it turns out that you can find it has anti-inflammatory properties. Now, we've done like 10 of these in my lab. Of course, you spin out a company because you're at Stanford. And this is my favorite one. This is my favorite one. This is one I was in the papers a couple months ago. This drug, imipramine, tricyclic antidepressant, it's still in the pharmacy, but we don't really use it much. We have serotonin reuptake inhibitors. This is against a disease called small cell lung cancer. Now, humans have to smoke to get small cell lung cancer. This mouse, you knock out these 3 genes, let's say they're P53, RB, P130, and it gets its own lung cancer. Barely you can see some of the nodules in the top left picture there. Now, this mouse on the right column was treated with imipramine. Now, we don't really use imipramine anymore because it had some kind of annoying side effects, right? It makes you really sleepy, and in some people, it sets you up to QT prolongation. It can set you up for an arrhythmia. Actually, neither of those 2 sound as bad as having small cell lung cancer. 5% survival rate in 5 years, okay? Essentially a death sentence when you're diagnosed. And on the right here, this mouse, the cancer is melted away. It's gone. It's gone in this mouse. Now, of the 10 that we've done, 10 plus, why am I showing you this one? Because it's my favorite. We start with public data. We get the idea. We test it in cell lines in a dish. I'm not even going to show you that. We get it working in the mouse model. That's great. 15 months after the computer prediction, 15 months later, we get IRB approval. We launch a clinical trial on this drug. There's patients on this drug now. I don't know if this drug is going to work or not in patients, but we have to try. There are not pharmaceutical companies working on this particular cancer, and they're not getting success. We're going to have to try to do this. And you know what we did in 15 months? The internal seed grant paid for the clinical trials, $50,000 for this trial. Not $50 million, $50,000. And that's in 15 months, and the next one we do, we got to do it in 12 months, and we got to do this faster, we got to do it cheaper, and we got to get all of us to do this, because we cannot keep depending on multi-billion-dollar drugs. If they're drugs that are essentially safe, that could be useful, we should try to extract every last use of these drugs that are out there. I think public big data can help us do this. So the other source of big data I definitely can't leave you without is that of DNA sequencing. Now, I'm not going to show you the double helix, okay? I'm going to show you this book, The Joy of Cooking, okay? This is kind of ethnic neutral, religion neutral book to use. How many of you have The Joy of Cooking at home? Yeah, almost a quarter. This is the definition of wishful thinking, right? We buy this book, we put it in the kitchen, it looks beautiful, we never even crack the book, we love the recipes, thinking they're gonna cook themselves, right? But a lot of people know The Joy of Cooking. It's 1,152 pages, and the joy, so when you think about your DNA, your genome, it's 6 billion base pairs, or 6 billion letters, 3 billion from your mom, 3 billion from your dad. If you take 6 billion letters, it's about 4,000 copies of The Joy of Cooking. So imagine 4,000 of them. Here are 200 of them. 4,000 of them would be 2.5 statues of liberty tall, if that's a unit of measurement that people can relate to. Just imagine all these books stacked up there. That is your genome in every one of your cells. It's essentially the same, whether it's a muscle cell, cheek cell, white blood cell, you know this. And obviously, these are recipes, just like your genome. The recipes in your genome obviously make protein. There could be misspellings. There could be entire chapters deleted. There could be pages all reversed. And it takes a lot of work and a lot of effort to figure all that out. Never mind figuring out what's the relevance of having a misspelling here. Some misspellings are okay, right? The British version of this book has the word spelled with British English. The American one doesn't. And that's okay. There's nothing wrong with that. But these are misspellings across the world, just like with DNA. So that's your DNA. It used to be sequenced in centers like this. This is a picture of the Whitehead Institute where I think this was taken around 2001. The genome project itself cost about $3 billion. It took 13 years. And now, within a year or two, we'll be sequencing it on a USB stick, okay? Here's an entire sequencer running off of the USB port of a computer. It's a no-brainer. This is going to impact medicine. Don't deny it, okay? It's just a matter of when. If it's running on your USB stick off of your laptop, you know we're going to be using this in medicine now. So current numbers right now, we had next generation sequencing, which is already previous generation 454 Life Technologies. Helicos had a $30,000 genome, which I'll mention in a moment. In my part of town, in Menlo Park, we have Pacific Biosystems, which is on track to sequence the entire human genome in 15 minutes. Okay, 13 years down to 15 minutes. That prompted Discover Magazine to have this article called The Jiffy Lube of the Genome, okay? Those of you who drive a car know Jiffy Lube promises to change your oil in 30 minutes. This will be 15 minutes and probably cheaper than that. For those of you counting terabytes, my friends at PacBio tell me they generate 20 terabytes of data every 15 minutes in their company. Just add up the terabytes. This is going to be an hour-long session here. That's, what's that, 80 terabytes of data just right there. Complete Genomics was on track to sequencing 80 genomes a day. That's one every 17 minutes if you do the math. They just got acquired by BGI. And I think the current record now is about $1,000 to $1,500 per genome. And there are big hospitals, children's hospitals in the middle of the country. I think Children's Mercy had a baby born in the NICU, and they got the entire genome back. They can get it back in 27 hours now. And with the whole interpretation, computing, not just the sequencing, that's pretty much the record now. This is the famous Moore's Law curve, if you haven't seen it. So what is Moore's Law? Back in the 1960s, Gordon Moore, as a founder of Intel, said computer power is going to double every 18 months. And you know what? He's been right. Another way to look at that is the same compute power drops in half every 18 months in terms of the price. If we were just following Moore's Law, we would be thrilled to pay $5 million per genome today. Right? Instead, they can't even keep this graphic up to date fast enough at NIH. We're down to the bottom at $1,000 per genome. And you just have to think about all the revolutions Moore's Law launched, like personal computers and internet and mobile and Facebook and Google. And you just have to wonder about all the revolutions DNA sequencing is going to launch in our field. It's going to happen. It's going to happen. And forget about in your lifetime. I'm not going to say in your lifetime. I'm going to say within the decade. The CEO of Complete Genomics had this blog post a couple years ago where he said he theorized that by the end of this decade, we will have it down to $33 per genome. I think I paid more than that for breakfast this morning at this hotel, right? You get the point, $33. What happens the year after it's $33? What happens the very next year? It reaches $0. And what happens the very next year? It reaches $-. What's a $- genome? Let me give you an analogy. There are literally car insurance companies in the United States that if you agree, they will ship you this little gadget to put under your dashboard, and it tracks your driving. It's got a GPS, it looks at your braking pattern, and if you don't drive like a maniac, they will reduce your car insurance rates. This is for real. Can we imagine any one of us doing this in medicine? You agree to get your genome, you agree to do some behavioral things, you agree to try to lose weight, we'll cut your health insurance rates. We don't need everyone to do it. We just need one to do it, and you're going to see what happens after that. Can we imagine someone do it? Of course we can imagine someone doing this. It's just a matter of time before this just becomes part of it. I know the legality and the ethics, but it's going to happen. It's going to be the numbers. So we were kind of lucky in 1999 to get one of the first patients to show up at Stanford with his genome. Now, he's an unusual patient in the top left there. This is Steve Quake. He started a company called Helicos. He paid $30,000 for his own genome, and then he showed up as a patient. Why? Because he's the red circle in his family tree, and the blue circle was his nephew, where one day at age 19, he died. He did not wake up one morning, had sudden cardiac death. So Steve Quake goes to his doctor, cardiologist, Ewan Ashley, says, "Doctor, am I going to have sudden death? Here's my genome." Right? And by the way, doctor, your next patient's already waiting for you in the waiting room. No one's ever going to give us more than 15 minutes to deal with this, any of us. So this whole exercise in the Lancet became a prototype of how we were going to deal with patients. Now it turns out, Steve Quake doesn't have any lethal known mutations in known genes setting him up for sudden death. He does know that he has a family history of coronary artery disease. We certainly confirmed that in the genome. So he'll have to lay low, maybe start statins at some point. He hasn't really started on statins, despite our advice. All this genomic advice, we recommended that he start on statins. He still didn't start on statins. We've yet to find the gene in the genome for compliance with medical care. And he definitely has the risk allele there, I'm sure of that. But someday he'll probably start on statins. Of course, the next thing we said, since we have his genome, what else would we do with this? Well, Russ Altman and his team could give a 2-hour talk. Of course, you can say something about 150 drugs now. Okay? Of course, warfarin at the top. Of course, we can do the dosing. Of course, with statins, the SLC01B1 variant, we know if he does choose to start on statins at some point, he's not going to get that kind of myopathy. And 150 other drugs now, more being added every week. This is just part and parcel what it's going to be like to have your genome. So you could say something about 150 drugs, even the most common drugs that are out there today. Then my lab, those two labs were kind of all taken. My lab was stuck with all the rest of medicine. Okay, heart taken care of, drugs taken care of. My lab was stuck with everything else in medicine. So we attacked this big data problem with another big data problem, and that of the literature. It turns out we realized that there was no master list of just every gene in the genome and all the different misspellings for diseases. So we just started to read the entire literature in genetics. We just reread every single paper. Because I run my lab like a startup company, I outsourced this to a company. We just read every single paper. Here's 1 paper, 6 papers, 100 papers, 1,000 papers. We've read almost 20,000 papers now, and now we know every single spot in the DNA associated with every single disease. And then we make graphics like this for Steve Quake. We call this a riskogram. And going up and down, top to bottom, are all the different diseases. The triangles indicate the risk from 0 to 100%. The triangles were what we thought your risk was. Not to be morbid here for a second, but we don't all start with 0 risk for disease, right? We're all going to die someday, even in this audience. I don't want to be morbid. Did you know in the United States, it's against the law to die without a disease? Did you know that? Right? If you fill out a death certificate, you got to put a disease on there, right? So even for one day, you're going to have a disease, maybe 1 hour, right? You're not going to be disease-free forever. You're going to die, you're going to have a disease. So there's some prior probability you're going to die of a disease, and so that's what the black arrows were. And the red lines or the blue lines tell us now that we have your genome, this is the new risk for the disease. And Steve Quake needs to watch out for coronary disease, obesity, and type 2 diabetes, as we told him here. Now, this is going to be a really negative interaction with healthcare if all we're going to do is say, you're going to die for this, you're going to die of that, or maybe you're going to die of that. They're not going to come back to see us again, right? But I think this enables what I think is the next big prescription pad of the future, and that is behavior and environment. Now, here's the same graphic, just shown a different way. Here, all the diseases are in the middle with font size, and all along the edge are all the known behavioral and environmental factors that influence the etiology of these diseases, okay? Because I think this is the new prescription pad of the future. So you can see in some of the big font, maybe at the top, Steve Quake, given your genome, you shouldn't smoke, you should exercise, you should watch your diet, and you probably should watch your alcohol. Probably didn't need a genome for those 4. Probably didn't need a genome for those 4. But in tiny font at the top, I'll circle it here, is Steve Quake, you're at slightly higher risk of Parkinson's disease. And 10 papers have linked the etiology of Parkinson's disease to pesticides. I don't make up these papers, that's what PubMed says. So Steve Quake, if you like to garden, you should probably stay away from the pesticides. Now this is crude. This is first pass, it's just a prototype. I think this is the way doctors and healthcare professionals can talk to patients about their genomes. Not with A's, G's, T's, and C's, but what are you gonna do to compensate for your genome? What can you do to alleviate the risk here? Now we did this for we did this for a family of 4. I'm gonna spend a moment on this family of 4 because they're an unusual family of 4. There's a mom, a dad, a 9th grader, and 11th grader. This is the next family we did. Now this father was really unusual. He was running a sequencing company too. He left the sequencing company, got his family sequenced for science fair projects for his kids. The 11th grader daughter presented twice at Cold Spring Harbor. She analyzed her factor V gene in Excel and presented this at Cold Spring Harbor, okay? So she gets a whole genome done. And what does she find? Well, she now knows her genomes, she knows her clotting genes. What happens is really interesting. I'm not giving out anything that's not under HIPAA here because they've talked to all the reporters, it's all in the press. The 11th grader becomes a 12th grader. She's gonna go to college. She gets really nasty acne. Goes to a pediatrician sends her to a dermatologist. The dermatologist said, boy, you know, your hormones are all over the place. You're going to college next year. Why don't we just start you on oral contraception, right? You're going to college next year. And what does the 12th grader say? Well, doctor, I am a compound heterozygote in my factor V gene. I'm a setup, right? Setup for a thromboembolism. Oral contraception is contraindicated in me. I can't wait for us to get to the day when every 11th and 12th grader can talk about their genome like this. I know this is an anomaly, but that's what we should be doing as an educator, right? And not being afraid of this, but adopting and going all the way, because kids are not afraid of that privacy stuff. If you haven't been on Facebook, you haven't noticed maybe, they're not afraid of that stuff. They maybe should be, but they want to take advantage of this and figure out what they should do differently to improve their health. Another kid that you should know is Nicholas Volker. If you just need to do anything when you leave here about genome sequencing, this is the poster child for genome sequencing. This is a child who was going to die because he was having bowel infarct after infarct killing his colon. And basically, as a Hail Mary pass, they got a genome sequence. His parents, they realized he had a new mutation in a gene for lymphoid tissue that was in lymphoid tissue. And with that, they gave him a bone marrow transplant. Now the kid actually goes to school, eats a regular diet. This is the first child saved with genome sequencing. Pulitzer Prize-winning story. Look him up after this if you're really curious. Of course, it's going to get bigger and bigger. Talk about new drugs and companies. Foundation Medicine IPOs with $1 billion valuation last year, taking cancer samples. It's not just going to be about the regular DNA, the cancer DNA. This is one of many companies. I'm not favoring one over others, but just to give you an example that a lot of therapy now in the future is going to be driven around mutations. You know about the melanoma drugs that are very specific for particular mutations. I'm guessing we're going to see more of those. And big data also comes from small packages. How many of you, just curious in this audience, have a Fitbit, Withings, one of these personal wellness? So maybe about 20 of those, maybe 40 in the audience. This is mine here. I used to laugh at these people. This is called quantified self. I used to laugh at these folks, measuring everything that comes in and out of their body. I guess measuring in is okay. Measuring out is kind of gross. But you can think about, you know, these folks are kind of weird, measuring everything. And until December 2012, I come back from a vacation in Hawaii. I'm weighing 247 pounds. And then I realized, if I hit 250, they can measure me in tons. That's 1/8 of a ton, right? Or something like that. Holy hell, I bought everything Fitbit makes, okay? Including the gadget on the right, on the left there, and the scale. And I'm putting it out there, that is my BMI curve. In the last 19 months, I've lost just shy of 50 pounds. I weigh myself every day. Hey, thanks. That's my BMI curve. I'm heading, you know, I got a while to go. The suits don't fit. I love it when they don't fit, but you can do it too. I got to write a book about this at some point, but I used to laugh at these folks and I realized you just watch it, you know, Weight Watchers rules, you bite it, you write it, put it into the app, and all of a sudden, it's, you know, principle, you're just looking at it, things improve. So I'm a huge fan of this. But you know what? As a doctor, this could be the most biggest thing to change my life. I don't have anything that talks to Withings or Fitbit right now. Big disconnect. How does that talk to Cerner, Epic, pharmacy systems? Nothing today, right? All patient run. It's all patient run. And then this company is just in my area in Palo Alto, Theranos. Any of you heard of Theranos? Maybe one or two hands. They're just changing how blood tests are done. I think they finally announced they got a $9 billion valuation or something like that. Crazy company building brand new headquarters in the middle of Palo Alto, which costs a lot of money. This tiny drop, just measure everything on a tiny drop. Instead of a blood stick, why not just get a finger stick, right? Oh, and by the way, it's not just the machines. Let's get it done with places with orchids. Let's make the nice kind of place to get the lab test done with nice flowers and orchids. And since we're putting orchids, why don't we just deploy all this in Walgreens, right? So now my patients as a doctor, I'm going to have to figure out they're going to Walgreens for their blood test. And by the way, the company just puts out the prices. CBC with diff, $5.35. I mean, the prices are on the website. Hell, I pay more than that for my latte at Starbucks today. You know this is going to disrupt everything. Now my hospital has to figure out how to talk to Walgreens. Whether it's Walgreens or Walmart, you know this is going to change. Oh, pharmacist, I have a question for you. What does it mean when it says that my CEA antigen is abnormal? You better start to learn the medicine here, too, if you haven't already learned it. Everything is changing in real time here. Oh, why even go to the pharmacist? Just get your own medical device at home, scan and do. This, medical tricorder, Star Trek fans, any of you in the audience, a couple hands go up. This little gadget, you put it on your forehead and measure your temperature, heart rate, pulse rate variability, transit time, oximetry. I guess you can pee on it because it does a urinalysis. I wouldn't pee on it, maybe I'll put a drop, I guess, at the top. Stress level. This is a homemade medical device. And how do companies get funding today? They put on Indiegogo and Kickstarter. That's where all cool new gadgets come in. They wanted to raise $100,000 over the weekend. So many people pre-purchased this, right? I put in my $200. I'm going to get one of these things someday. They raised $1.6 million over the weekend. And here's a medical device now, right? Just like that, over the weekend, they have the funding to do it. Where does this data go and live? I don't know. It's a whole new player again in healthcare. We got the apps, GoodRx, right? I'm standing. Where should I buy my simvastatin? Well, CVS has it for a little bit cheaper than Walgreens. But if I switch to the generic, oh, well, CVS with this, I got $10.75, but Walgreens with this coupon, click here, I got $10. This is for real. These aren't made up apps. You stand in the middle of a city, you're going to spin around and figure out where's the cheapest pharmacy today for your drugs. For the hospital, right? I did this when I was in San Antonio the other day. If I were to have crushing chest pain right now, which hospital should I tell the ambulance to take me to? Well, in the downtown San Antonio, you can see there's B and C hospitals right where that blue dot was, but there was an A hospital on the bottom left there, right? So I can, I guess, merge that with the traffic. Oh, there's no traffic. Crushing chest pain. Take me to the A hospital. Don't leave me at the B and the C hospitals here, right? Let's just merge that with the traffic on my phone. And my favorite is the Clean Hospital Finder. This app asks patients to report whether the patient in the hospital has seen anyone clean their bathroom today, right? Searching, here it is. Well, not even all the B hospitals clean their bathrooms. Oh, thankfully that A hospital on the bottom left there does clean their bathrooms, right? This is all there today. I'm not making up any of these apps. This is healthcare. Of course, you might have seen last year, the FDA now regulates apps. Did you know this? FDA already regulates 200 apps. Well, it's kind of borderline there. If the app talks to a medical device, they regulate the apps now. Okay, amazing, FDA and apps. The pricing data, I know you had Ian here yesterday. I'm not going to spend anything more than this. This was embarrassing because I was giving grand rounds at the University of Miami. Sorry for anyone from Miami here. But this showed up in the Washington Post front page. University of Miami charges double what Jackson Memorial does across the street. If you don't know what your pricing data is, you better learn it before the reporters do, because it's all transparent. If you didn't get that message yesterday, I'll just resonate really loud. Now all of a sudden, we love being outliers in the US News and World Report. You don't want to be outliers here anymore. You want to be in the middle of the pack, right? Not too much, not too little here. The doctor's fees are now out there. The oncologists are just getting burned because they pay for the drugs and then dispense the drugs. No one wants to be that high anymore, right? But it's all going to be transparent today. The next big data that I think is going to be changing the world is clinical trials. Clinical trials. Just heard about clinical trials from both of the award winners. What is a clinical trial? The most expensive experiment in the world. It's part of the reason why it's costing billions. And half of them fail. And we got this weird culture when a clinical trial fails, we don't even write a paper about it. Forget about sharing the data. I think it's going to change. First, it's going to be the editors, and then it's going to be the funding agencies, and then it's going to be the government requiring this trials data. I run something called Import. We've already put out to the public 100 raw clinical trials data. I don't mean the summary stuff in clinicaltrials.gov. Raw clinical trials data is going to come out there. What that means as a platform, it's brand new. And then we got this data. We have so much data, we play games with it. I want to leave you with this kind of frightening point. Heritage provider, of course, we all know, we're trying to predict readmission rates, right? Because if a patient gets readmitted within 30 days, that's woe for us, because we're not going to get paid for that admission. We all know that. These guys 2 years ago realized that, and they said, well, let's get all the best minds, give them all of our raw data, and have them come up with the algorithm. And whoever wins, they're going to win a $3 million prize. Okay, so you can see at the bottom right there, 1,800 teams competing to come up with the best algorithm to predict admission, right? Given demographics, ICD-9 codes, and everything. Now that top 10 leaderboard is that night because they recompute it every night. Now there's something kind of magically frightening about this way of doing business in healthcare. First of all, this idea of running competitions came from Netflix. I don't know how many of you know Netflix before all the streaming, they gave out CDs and DVDs. Now they don't even do that anymore, I think. But these competitions are going to be changing the world. In fact, there's so many competitions now. There's a company in the Silicon Valley now that actually just runs the competitions for other companies called Kaggle. Now, why is this frightening to me in academia? How do grants work today? We propose to do something, and they give us millions to do it. We hope NIH and the government doesn't figure out, maybe they should just pay the winners, right? We should all be doing the work for free, and then they pay the winners. Kind of hope the government doesn't figure this out. Oops, the government has figured this out. It's called challenge.gov, 10,000 challenges. They give you tens of thousands of dollars if you're the winner here. What an amazing world. It's changing in real time. Even how we get grants are going to change. And the data comes on and on, EHRs, MedWatch, FDA, and all the rest. Now, in the last couple seconds, I just want to calm you down, the ones that are frightened by all this. How on earth are we going to expect healthcare professionals to review 6 billion pieces of data in a 15-minute encounter? How are we ever going to do that? Well, actually, we do have some healthcare providers that actually do this today. We have healthcare providers that review a gigabyte of data in 15 minutes. We actually call them radiologists, right? A radiologist or an ultrasound technician, when they're looking at their pictures, they're reviewing a gigabyte of data in 15 minutes, but we give them tools to do this. So it's going to be a brand new era of tools, computer tools, software tools, mobile tools. We're not going to be looking at it base pair by base pair. We're going to have tools to do. So rest reassured, okay? We're going to have those tools, but also see the opportunity. It's up to us to come up with those tools. That's going to come from our graduate students. It's going to come from our folks in academia. And some of them will have to launch companies to do this because NIH can't pay for all this anymore. Right? It's going to come from the private sector as well. So in the last second, what is big data in biomedicine in the end? Is it about algorithms, programmers, cloud computing, whatever the cloud is, databases, high-performance computers, or mobile? It's not about any of this. Big data in biomedicine is about predicting diseases before they strike, explaining rare diseases that defy experts, finding drugs for diseases that lack attention, making sure we do the right, safe, cost-effective thing for patients, and happens to be an amazing platform for biomedical innovation and entrepreneurship. And I could sum all this up with one word: hope. Big data and biomedicine, in my view, is the way that we're going to deliver hope to patients, to healthcare providers, to a pharmacy, to a pharmaceutical company that's spending billions today. I think we have a lot in the future here. And I hope some of you will get the idea to join us because there's plenty of data to go around here. I can't do any of this without a long list of collaborators, too numerous to mention. I'm blessed with endowment support from the Lucille Packard Foundation for Children's Health. My lab is blessed with 17 NIH grants from these 9 institutes of NIH. The ones on the left give me more. The ones on the right give me less. I still love them. March of Dimes, HHMI, a lot of disease-specific foundations give us money now to study their diseases. I always thank my admin and tech staff. I'd never get a grant or paper out the door without them. And I always thank my wife, Tharangini Deshpande, a biochemist, molecular biologist who now starts companies with me, reads all the big papers and grants that come out of my lab, and lets me go all over the place to give talks like this. Thank you very much.
Thank you. Oh my gosh, that was just wonderful. Oh my gosh.
I think I left a couple minutes for questions, right?
A couple of minutes for questions. If anyone has questions, please rise. They're all shocked.
They're also starving too. I will definitely be hanging out up front here because I think people are a little too shy here. There's a question coming up in the back here. Hold on.
Oh, good.
He's going to a microphone.
Great talk. Thank you very much.
Thank
Paul
you.
Hudson from the University of Wisconsin-Madison. So as we are looking at changing curricula to deal with the new environment, what kind of skills would a pharmacist or a physician, nurse practitioner ideally have? You know, we're not going to be necessarily the ones writing these tools that you refer to for the radiologists and so on.
That's right.
What skills should we be looking to create or provide the option to our students?
Yeah, so the question, just to repeat, is what do you do in terms of pharmacy education to really deal with this field? First of all, I think you want to make sure, even before they come to pharmacy schools, that you don't lose the quantitative thinkers in the beginning. right? A lot of these folks, even in high school, they start to write apps. They think that they're just going to go to a company like Google or Facebook, and that's great, but we need some of them to come to our fields as well, okay? So don't say no to those quantitative thinkers. When they come in, give them every opportunity you can. Get them involved with data science projects. Look, some are just going to be pharmacists, right? But the ones that are going to be leaders are going to think about reinventing the field. I think so much is in topsy-turvy right now in healthcare that we all have an opportunity to reinvent our fields, including pharmacy. What does it mean? Are patients going to show up to the pharmacist with their genomes? Are you ready for that? Or does it have to go through the doctor? If a patient comes with a 23andMe report today, what do you do? I know what we do in medicine, we kind of ignore them. We don't want to even talk to them about that. Is that what you want to do too? I don't think so. So I think it's really about reinventing your field today because everything's getting reinvented right now. I think you want to instill that kind of entrepreneurship and innovative thinking into your students as well. There's a couple questions. Okay, go ahead. Yep.
So, Butte, this is Xiu Wu. So, if you demonstrate some conclusion you conclude from your big data, are you going to go back to the laboratory or clinical trials or animal study to repeat?
Yeah, that's a great question. When you have these findings in big data, what do you do next? You have to validate some of these findings, if not all of these findings. Just because you get a correlation doesn't mean causation, as you all know, right? You've known that for decades. So a lot of times that means repeating or just going back to the lab in a very targeted way. I have a particularly weird way of doing that because I outsource my wet biology experiments. If you're really curious, I have lots of YouTube videos on that. But you do this with collaborators, you do this with colleagues, but you have a finding, you have to validate this. Now that doesn't mean you have the opportunity or even finances to run every possible clinical trial. So there are going to be limitations to that approach. But sometimes you might learn something from one set of data and kind of validate it in another set of data. So biological experiment because we have so much big data out there. There's a question here in the middle.
Thank you. Here's Jeff Kuo from University of Cincinnati. Very informative, very exciting. You leave the question, but I would like to have a clue that we need to have a tool to read all this big data in terms of pharmacy. What kind of a tool or what elements for that new tool or many tools, what elements can you allude to us?
Yeah, it's a great question. So it's also about the tools. And right now, specifically for the field of pharmacy, there are probably no tools to analyze this kind of molecular data or systems level data. There are consulting practices that have their own tools to help at least guide strategy and things like that. But there are no tools for academia right now. I think the opportunity is for all of us to create these tools. I mean, that's why now maybe you have an idea why so many of my grad students start companies, right? They see the data, but before you develop the tool, you got to figure out what can I do with this data. 99% of this is not the tool. It's not about the computer. It's realizing, oh, I have this data. Now I can answer this question. If you can answer a question with this data, probably 100 others want to answer the same question with their data, and that means that you create a tool from this. So I think the hardest part is realizing this data helps you answer a question. You don't need to collect new data because you already have the data. That is 99% of the work right now. I think there's one more question in the middle here.
Okay, very nice talk. Quentin Smith from Texas Tech. You gave one example of where you were using the genome to make predictions on future disease and predisposition. And then I think a company, 23andMe, was doing some, and FDA stopped them. What was the difference there between what you're doing and what they were doing?
Absolutely, great question. So he's mentioned about 23andMe, which got into trouble with FDA, particularly for direct-to-consumer marketing of genotyping testing. These are controversial days right now. They particularly got in trouble. So I'm a literalist, right? If you read the letters from the FDA, I'm reading them literally. And in the letters from the FDA, it says, we tried to call you, but you didn't return our calls. Probably always a bad idea not to return the calls of the FDA. So that's a literal interpretation. There are others with a more expansive interpretation thinking that FDA is against genome sequencing, yet all the time, every day, we're still measuring genomes, we're looking at genomes. So I think it's still cautious what you give directly to lay public. Right? In this particular story, I'm telling you, we're working with healthcare providers, right? So we're not going directly to the public at all. But there's at least an interpretation from a healthcare provider. That's a loose definition there. I think it's still early days to figure out what's going to happen next year. But I will tell you, the lay public, I mean, look, again, I have no connection with 23andMe, but what I read in the papers, 700,000 people have already gotten their genotyping done, right? So that's an amazing number. You know, they see it on Oprah, they want to get their genotyping. Whether they got value or not is another whole story. But for $99, again, that's a nice dinner around here, right? So it's not a lot of money either, right? And no cost to payers right now, so.
Thank you.
I think that's the last
I
question.
think
So
that's it.
great. Thank you very much.
Bye-bye. Thank you. On that note, we will have to wrap up. Another round of applause for our terrific speaker. I have just a few announcements before we close. Remember, as an annual meeting attendee, you can access all recorded sessions posted in the AACP Online Learning Center. This includes more than 50 hours of continuing education. Before you leave, please note the CE code on the screen and follow the directions in your program guide. This concludes the Science Plenary. Please enjoy the rest of your day. Thank you.